Here we're told we have a piston cylinder assembly containing carbon monoxide modeled as an ideal gas. So let's just sketch that out. Here's our cylinder, there's the piston, we've got carbon monoxide in there, and then we'll make the carbon monoxide our system. And we're told that it has a constant specific heat ratio of 1.4. The carbon monoxide undergoes a polytropic expansion with N equal to K from an initial state. So what that means is a polytropic expansion, so a polytropic process, means that PV raised to some power, it's the volume that's raised to the power, to the nth power, is equal to a constant. So that's what a polytropic process means. It means that the pressure and volume are related to one another using that expression, where here the N is equal to K, which is equal to 1.4. So I'll just make a note of that here. N is equal to K, which is equal to 1.4. From some initial state where the temperature and pressure are given to a final state where the volume is twice the initial volume. So I know that V2 is equal to 2 times V1. And we're asked to determine the final temperature and final pressure in the carbon monoxide and the work done by the gas and the heat transfer into the gas. So there could be some heat transfer coming in. I'll draw it in my energy flow diagram like that, and there's some work being done by the system on the surroundings, so I'll draw that as well. Now, in this polytropic process, we have a constant, and the way I can find that constant is from the initial conditions. I'm told the initial temperature and the initial pressure. So I can just write, PV to the N is equal to P1 V1 to the N, right? Because I know that since it's a constant, it'll be the same constant at the initial state. It's also the same constant at the final state. So I can do that as well. Okay, so in order for me then to find what the volume is, so I'm given what the initial pressure is and the initial temperature, but I don't know the initial volume. So the way I'm going to find that is from the ideal gas law. I'm told that the carbon monoxide behaves like an ideal gas law given the pressure and the temperature. So I'll just make use of that ideal gas law to find the initial volume. Okay, so I'll just write PV is equal to MRT. That's just the ideal gas law, or you can also write it in terms of specific volume, just like that. P specific volume is equal to RT. And then I'm going to combine this expression with the polytropic process. So what I'm going to do is I'm going to write the ideal gas law for, take the ratio of the before and after. So let me do it this way. And I'm going to just divide it by the kind of the after state. Move the equal sign around here. Okay, so you'll see the reason I'm doing this is because I'm just trying to get rid of the gas constant and the mass. So you'll see the mass remains constant in this process. Gas constant, of course, is a constant, so I have that. And then I'm going to also make use of this polytropic process expression as well, and just substitute that in for the pressure down here. So I can write here pressure is equal to this constant. Let me just call it C for convenience, divided by V to the minus, or V to the N, so that this expression will become, let's see, it'll be the constant times V1 to the 1 minus N over the constant V2 to the 1 minus N is equal to T1 over T2. You see the constants cancel out as well. And so then the final temperature, T2, would be T1 times, it'll be what, V2 over V1, all raised to the 1 minus N. Just make sure I've done my math correctly there. Okay, so now I'm given some information here, right? T1 was 200 degrees Fahrenheit. I know that V2 over V1 is equal to 2, right? That was given in the problem statement. It says the volume, final state has a volume that's twice the initial volume. So that's where this comes from. V2 over V1 is equal to 2. And then the n, we're told, is equal to 1.4. So I have all the information I need to do this calculation. And when I plug in the numbers, I'll get that T2 comes out to be 500.2, or just 500 degrees Rankine. By the way, when you do this calculation, you should use not 200 degrees Fahrenheit, but you should convert that over to degrees Rankine. And that'll come out to be about 660 degrees Rankine. And the reason you want to do that is because you're taking a ratio here. Whenever you're taking a ratio, you need to use absolute values. So you need to use the absolute temperature, not degrees Fahrenheit, but use degrees Rankine. So that comes out to be 500 degrees Rankine, and of course you can convert that over to degrees Fahrenheit. That comes out to be 40.2 degrees Fahrenheit. All right, so that's really just what I did was I just took a combination of the ideal gas law and combined it with the expression for the polytropic process. I just combined those two together to arrive at this expression. That's all it is. Okay, now that I have that expression for, or now that I have the temperature, let me go ahead and calculate the final pressure. Okay, so to find the final pressure, what I'm going to do is just use this expression right here. This just comes from the polytropic process. So I can just rearrange that and get P2 is equal to P1 times, this will be V1 all over V2 raised to the n power. Okay, so all I'm doing is just using this expression again, the polytropic process expression, just rearranging down here, making use of the fact that V2 is equal to twice V1. That's just given in the problem statement. Again, I know P1, that's given, I think that was a 40 psi 8. So that means it's already an absolute pressure. Again, we want to use an absolute pressure because this is like a ratio, P2 over P1. So you need to use an absolute pressure, just like we needed to use absolute temperatures here. And then the V2 and V is known related to V1. N, of course, was 1.4. That's given in the problem statement. So then you can calculate that P2 comes out to be 15.2 pounds per square inch absolute. Okay, so that part of the problem, it was just a matter of making use of the polytropic process relation along with the information we're given about how the volume changes. Okay, so that's good. We've gotten part A completed. Now let's do part B. This is finding the work done by the gas and the heat transfer into the gas. So for these, to find the work, I'm just recognizing that this is a PDV type of work. You know, we're doing work against a moving piston here, so I'm going to find the work using PDV work. The heat transfer, I'm going to use the first law to find that, because once I have the work, I can combine that with an I'll need to calculate the change in the internal energy, but if I have those, then I can find the heat transfer from the first law. So that's where I'm headed. Let's find the work done by the gas first. So that's PDV work, so that's going to look like the following. Just the integral of P times dV as we go from the initial volume to the final volume. And then I can use the expression for a polytropic process to substitute in to get the pressure in terms of the volume. Remember, the pressure is changing here with the volume, so we need to be able to express the pressure in terms of volume here. So this will just look like the constant times the integral of V1 to V2 of V to the minus n dV. The constant we can always evaluate using the initial state, so that's equal to P1 times V1 to the n, because we know the initial, we could just use the initial state conditions for that. Okay, so let's go ahead and evaluate then the integral. Let me do that down here. So this will be P1 V1 to the n. This will be 1 divided by 1 minus n times b2 to the 1 minus n minus b1 to the 1 minus n. So I'm just integrating. I can do this integral because I know that n is equal to 1.4, and this is just a kind of a straightforward way, you know, just kind of the normal integration that you've done many, many times in like a calculus class. If n was equal to 1, then that integral would be a natural log. But if it's not equal to 1, it's just it's an integration of something raised to a power. It's pretty straightforward. All right, so we have this expression. We're not exactly given the volumes, and we're also asked in particular to find the work done by the gas per unit mass. You can tell that just from the units. BTU, that's a unit of energy, and then pound mass, of course, is a mass. So really it should have said work done by the gas per unit mass and the heat transfer into the gas per unit mass. So since it's per unit mass, what I'm going to do is I'm just going to divide both sides through by the mass. Sometimes we get that the symbol little w. So that's called the specific work, or the work per unit mass. And if I do that, that means I just need to divide the right-hand side through by the mass, which means that it'll convert these volumes into specific volumes. So this would be like P1 times the specific volume at 1 raised to the n. There's the 1 minus n, and then this will be multiplied by the specific volume at 2 to the 1 minus n, minus the specific volume at 1 to the 1 minus n. Okay, so that's where we are currently. Now, we don't know the specific volumes yet, but we should be able to find those from the ideal gas law. Remember, from the ideal gas law, we have P times specific volume is equal to R times the temperature. And we know, for example, at state 1, we know what the pressure is, and we know the temperature, so we should be able to find the specific volume at state 1. Just keep in mind that this gas constant here, R, is the gas constant for carbon monoxide. That's our working gas here. We're told it's carbon monoxide. So we need to look up or calculate what the gas constant for carbon monoxide is. And the way you could calculate it, for example, is you would just take the universal gas constant and divide it through by the molecular weight or molecular mass of carbon monoxide. So just to kind of give you a feel for how you do that, if you look up the universal gas constant in these kind of crazy English units, it's 1.986 BTU per pound mass mole. Per pound mole is just a common way to say it. And then also there's a degrees ranking in the denominator there. So that's the universal gas constant. And then to find the molecular mass or molecular weight of carbon monoxide, you would refer to the periodic table. And what you'd find is that the molecular mass of carbon is 12.011 pound mass per pound mass mole. And then the molecular weight of oxygen is 15.999 pound mass per pound mass mole, or pound mole, if you want to call it that. Okay, so what I did is I just went to the periodic table and looked up the molecular mass of carbon. There's one carbon, so I have just one of those. And then there's one oxygen, so that's there. So you add up the molecular mass of each of those atoms to get the molecular mass of the molecule. So that's what that is. So here's how you can calculate what the gas constant is for carbon monoxide. And when you do that calculation, it comes out to be 0.07090 BTU per pound mass degrees Rankine. Okay. So anyway, that's how you'd get that calculation there. So to find the specific volume, for example, at state 1, we'd have that gas constant for carbon monoxide times the temperature at state 1 divided by the pressure at state 1. And so you can do that. We're given the pressure is 40 psia. You're given the temperature is 200 degrees Fahrenheit. There's going to be some unit conversions involved. The pressure is already an absolute pressure, so you don't have to convert that over. But again, the temperature you want to convert from degrees Fahrenheit to degrees Rankine. And then there'll be some unit conversions that you have to do in between. I'm not going to go through those here, but just be aware that you have to be careful with the units. So just write those out if you do this calculation on your own, and just verify that you've got all the units correct. But that comes out to be 8.124 times 10 to the minus 3 cubic feet per pound mass. And then we, of course, know that the specific volume for 2 is twice the specific volume for 1, since the mass isn't changing, and we're told the volume is twice the initial volume. So that means V2 is going to be 1.625 times 10 to the minus 2 cubic feet per pound mass. So now that we have the specific volumes at states 1 and 2, we can go back up here and plug them in here. Here, we know the value for N, that's just 1.4, and we also know the value for the pressure at the initial state. And then you have to, again, be careful of some unit conversions, but when you go through all those calculations, you'll get the work per unit mass as 28.3 BTU per pound mass. Okay, so that's a matter of being able to calculate PDV work and just making use of the polytropic expansion expression, just substituting it in, doing a little bit of calculus, making use of the ideal gas law to find the specific volumes. You got to do a little calculation here to get the gas constant for carbon monoxide, and then a bunch of tedious unit conversions, which is just something you have to do when you deal with these English units, unfortunately. But that's easy to make mistakes with the English units, so it's worthwhile to write them out. I'm just not going to do that here for the sake of time. Okay, now as far as finding the heat added to the gas, I said I was going to use the first law for that. So the change in total energy of our system, which is our carbon monoxide, is equal to the heat going into that carbon monoxide minus the work done by the carbon monoxide. This one I just calculated. Oh, and by the way, we're doing this all per unit mass, so I should just write this in the following way. I'm just using a lowercase set of values. So, for example, we said the work is the specific work. Let me rewrite that. The specific work is the work divided by the mass. The specific heat transfer is the heat transfer divided by the mass, and the specific total energy is the total energy divided by mass. So that's what I've done to go from here to here. Now, the work per unit mass I just calculated. That's right here. So that part's good. The Q into is what I'm trying to find. Let me now expand the change in specific total energy. That's going to be equal to the change in specific internal energy plus the change in specific kinetic energy plus the change in specific potential energy. Since our piston cylinder arrangement isn't changing its velocity, change in kinetic energy is going to be 0. It's not changing elevation, so the change in potential energy is going to be 0. So the Q into will be U2 minus U1, which is just our change in specific internal energy. Okay. Now, at this point, what we have to do is now find what the, oops, I'm sorry, I made a mistake there. It's the U2, oops. It's going to be U2 minus U1, and then I have the plus the specific work, right? Because I have to bring this one over to the left-hand side, so that I forgot that one when I wrote that out. Now, to find the U1 and the U2, what we can do is we could go ahead and look those up in a table. So since we know the temperatures at the initial and final state, remember we're given the initial temperature and we calculated the final temperature, so I could use an ideal gas table for carbon monoxide to find those. Remember that for an ideal gas, I know that the specific internal energy is a function only of temperature. So U2 would just be the specific internal energy at T2, and U1 would be the specific internal energy at T1. So I could go to an ideal gas property table for carbon monoxide and look up the values for these specific internal energies at those temperatures to get these values. And let me just see if I actually, yeah, I did look those up, and I'll just give you the values. So U1 comes out to be 117.0 BTU per pound mass. I'm not showing you the table to look those up. Hopefully you've done enough problems on your own to know how to use the tables to find these values. By the way, depending on the table you use, you may end up looking up the specific internal energies in terms of BTUs per pound mass mole or per pound mole. And the way you convert it over is the following. To get the specific internal energy in BTUs per pound mass, it would be the specific internal energy in terms of BTU per pound mole, or pound mass mole, divided by the molecular weight. Let me erase that line, make it better. Divided by the molecular weight of the carbon monoxide, which would be in terms of pound mass per pound mass mole, or pound mole. And we already calculated the specific mass or specific weight right up here. So that's what you would use here. So the table that you use may give the specific internal energy on a molar basis, which is this. And so to get it to this set of units, this is the conversion or the calculation you'd have to do. But anyway, I went through the table, did a little interpolation, did this type of calculation, and got those values. And then what you get in the end is Q into, comes out to be minus 0.16 BTUs per pound mass. So it's a very small heat transfer. And in fact, the heat transfer is out of the system, not into the system. So when we look at the arrow that I drew here, I show heat going into the carbon monoxide, but actually the energy is coming out because it's a negative value. It's a very small amount. Right? Certainly it's much smaller than what the work is. Now another way that we could have done this calculation is to, instead of using the tables, if we make the assumption that the carbon monoxide is a perfect gas. Okay, so a perfect gas is an ideal gas plus constant specific heats. So that means that instead of the specific heat at constant volume being a function of temperature, it would in fact be just CV as a constant. That's what we mean by constant specific heat. So in that case, U2 minus U1 would just be CV times T2 minus T1. We know the temperatures. Now to get the specific heat at constant volume, that you'd have to look up in a table, and that's exactly what I did. I looked it up in a table. It came out to be 0.178 BTU per pound mass degrees Rankine. And I looked it up for a specific, in general, we know that the specific heat at constant volume is a function of temperature. So you might ask yourself, well, which value of CV do I use? And my suggestion is to use a value of CV close to the temperatures that you have in the process. So it's going from T1 to T2. If you look at these temperatures, we're going from 200 degrees Fahrenheit down to 40 degrees Fahrenheit. So a temperature somewhere in between those seems pretty reasonable. So I chose a temperature of 100 degrees Fahrenheit. It's just somewhere in between. Okay, so this is at 100 degrees Fahrenheit. So that's how I arrived at that value. Because remember, we're assuming here that it's a perfect gas, so its CV is a constant. So if you make that perfect gas assumption, then you do your calculation Q into, it would come out to be minus 0.11 BTU per pound mass. So, it's pretty close to what we calculated using the more accurate tables, but it's not the same. There's some error. So, using the perfect gas assumption here, we're off by, what is that, like, 0.05 out of 0.16. So what is that? That's roughly 1 over 3. So we're off by about 30% here. That's a pretty big error. So that might not be acceptable. You're always better off using the ideal gas tables to get the most accurate answer, because those ideal gas tables take into account the variation of the specific heat with temperature. So this is the more accurate value. Doing the perfect gas assumption gives you a less accurate value. You can see here we're off by about 30%, so it's not as good. So doing this perfect gas assumption is sometimes handy if you don't have access to the tables, but it's not going to be as accurate as using the tables. Okay. All right, I think that covers everything we needed in this problem. Let me just go back up to the top here and just double check. We found the work done by the gas and the heat transfer to the gas in terms of BTU per pound mass. So yeah, we've done everything we need. So just a quick recap. We made use of the polytropic process expression, ideal gas law. We had to be careful of unit conversions. We did PDV work, knowing that we're dealing with a polytropic process. Also made use of the ideal gas law here, found the gas constant using the universal gas constant and molecular mass. And then we also made use of the first law to find the heat transfer per unit mass, as well as using the ideal gas tables. All right, so we'll end the example there.